चलो ठीक है। ये इसके लिए आप अपने बॉक्स ले जाओगे, पैनकेक लेना हो तो खाली पैनकेक तो अच्छा है, वो लेना है, कुछ तो लेना, सुबह सुबह कुछ तो खा लीजिए। कोई नहीं, फ्रेश रहेगा, थोड़ा अच्छा लगेगा, उसको अच्छा लगता है, यहाँ का पैनकेक अच्छा होता है, मुझे सोची जाऊंगी इसके लिए ले आऊँ। और इसलिए घर का खाना खिला
Hello everyone, welcome to week 11 live session of NPTEL Semiconductor Device Modeling and Simulation course. I am Om and today we'll be solving some questions that may help you in your exams as well as assignments. So let's start. So mainly we'll focus in this week on the Schrodinger equation, solution of Schrodinger equation, potential step, potential barrier, free particle system and tunneling. So let's just start with a brief overview of the Schrodinger equation that we will be using. So we will be using time independent Schrodinger's equation, and this is given as minus h cross square by 2m del 2 psi by del x square plus u psi equals to e psi. This is the time independent Schrodinger equation where psi is the wave function. This is the kinetic energy of the system. This is the potential energy, and this e psi is the total energy. So this is a very simplistic 1D time independent Schrodinger equation, and psi is the wave function. So there are some restrictions on psi. Psi is the solution of Schrodinger equation, and psi must be continuous. Psi must be differentiable, which means d psi by dx is defined, and d psi by dx must also be continuous and differentiable. That is, d2 psi by dx square is also defined. And lastly, psi must be normalizable. That is, minus infinity to infinity mod psi square dx is 1. So now let's try to solve the Schrodinger equation for a simple particle in an infinite well. Sorry, is the what is needed? Proof. What proof? There is no proof for Schrodinger's equation. Yes. Okay. So let's see how we can apply this to for a particle in an infinite well. So infinite potential well, let us assume we have a potential well like this, where here potential is infinite and here potential is 0. This is x equals to 0 position, this is x equals to L, and your particle is inside this. So you have some non-zero wave function here, and wave function here will be 0. So these are the boundary conditions that we will be using. So we can write the potential as 0 for x, and potential is infinite elsewhere. Similarly, we can write the wave function as is 0 when x is less than equal to 0 and x is greater than equal to L. We have to find what is the formulation of psi inside this between x equal to 0 and x equal to L, elsewhere it is 0. So if we rewrite the Schrodinger's equation, so between 0, x and L, your u is 0. So if we substitute this, now if we rearrange, okay, so let's just replace this constant with k square, that is del 2 psi by del x square equals to minus k square psi. K is under root 2 me upon h cross square. So k is actually your momentum in the ek curve, right? This is the momentum vector. So the general solution to this equation is psi x equals to a sin kx plus b cos kx. Now at x equals to 0, we know that psi is 0. Substitute this. Sin 0 is 0, cos 0 is 1. And we know this psi is 0. What? Yes, which is also equal to 0. That means b is 0, right? Because psi at 0 is 0, so b will be 0. So your equation now becomes psi x equals to a sin kx. Now the second boundary condition at x equals to L, psi of L is 0 again. Psi of L equals to 0 equals to a sin kl. So for this condition, this means kl equals to n pi, k equals to n pi by L. So yes, we derived this, right? Psi x equals to a sin kx. I just put L here and here. What? Hmm. Yeah. Why will it be different? What is the difference? But we have already found out, right? B is 0. No, this is for, and from the boundary condition, we found out this constant. The constant value is not changing. These are the constants, right? We are trying to find the values for this constant using the boundary conditions. So B we already found out that it is 0. A we are trying to find out now. Yes. It is psi x. L is your constant. So this is your psi x. But we still do not know A. But we know the solution is of this form. So to find A, we'll use the normalization condition. Minus infinity to infinity. Mod psi square dx is 1. And since our system is defined, on psi is defined only between 0 and L. So we'll reduce it to 0 to L mod psi square dx is 1. So we put this value 0 to L a square sine square n pi x by L dx is 1. So a square, let's take out 1 minus cos 2, 1 by 2, sorry, 2n pi x by L dx equals to 1. Now integration of cos n pi is always 0 because cos becomes sine and sine n pi is 0. Yeah. So this will be 0. We will be left with a square by 2 x integration 0 to L is 1. So simply a square L by 2 is 1. This means a is equals to under root 2 by L. So we have found a also. So now your the function finally is under root 2 by L sine n pi x upon L. This is your solution to the for particle in a 1D infinite potential well. Now we can also see the energy of the particle. So to see that we have two relations. One is this one, k is equals to n pi by L. Another one is this, k equals to 2me by h cross square. So if we equate these two, we have k equals to under root 2me upon h cross square. And we also know k equals to n pi by L. So if we equate these two, we will get E equals to n square pi square by L square h cross square by 2m. So this is your E. Okay, so these are the wave function and energy of particle in 1D infinite potential well. Okay, so let's start with the question now. The first question is, consider an electron in a 1D infinite potential well of width L, H is at equals to 0 and x equal to L. It's similar to like what we had just considered. X equals to 0, x equals to L is infinite here and 0 here, potential. Now calculate the probability of finding electron to be present between x equal to 0 and x equal to L by 4. So we need to find, okay, so this is actually the probability of finding electron, right? Yeah, normalize this condition. This one means actually this size mod psi square is the probability of finding an electron, and if we take it over the whole range of x, the probability of finding electron will always be 1. And we know we just calculated between 0 to L, this probability of finding electron is 1, but now we have to find between x equal to 0 and x equal to L by 4. So let's do this. So we know that psi of x for this infinite potential well is, yes, what? This we just found out, right? Psi x for this infinite potential well, psi x is under root 2 by L sine n pi x upon L. Now they have given assume n equals to 1, so we will take n equals to 1 now. So if I just remove this n. Okay, now we know that we have to find 0 to L, L by 4 mod psi square dx equals to question mark. This is what we have to find. So if we substitute psi here, 0 to L by 4, 2 by L sine square pi x by L dx. This is what we have to find. Let's call it probability p equals to. Now this 2 by L I can take outside, and L by 4 sine square n pi x upon L I will substitute bit 1 by 2 1 minus cos 2 pi x by L dx. This 2 and 2 will cancel. This is 1 by L. Now if I integrate this, it will be x. Sorry. Okay, let's solve this. X minus, no, why will it be 0? Yeah, but you see now limit is not 0 to L, it is L by 4. So you will not have 2 pi term now. You will have some pi by 2 or something. So we need to solve this. So integration of cos is sine 2 pi x upon L, and this constant L upon 2 pi. Limit is 0 to L by 4. We substitute this L upon 4 minus L upon 2 pi. L will cancel. This is 1 by 4 minus 1 by 2 pi. And if you solve this, it will be approximately 0.09. Yes. Yes. If we put this will be sine 2 pi L by 4 upon L. So this will cancel. This 2 will be, so it will be sine pi by 2. Sine pi by 2 is 1. So just, and at 0, both will be 0. So answer is option C. Okay, so let's see the next question then. Yes. So which of the following conditions are satisfied by the valid wave function? So psi must be discontinuous. This is incorrect. It must be continuous. Psi should also be single valued. And if it is continuous, it will not have these abrupt changes. And psi must be normalized. It is the correct one. That is minus infinity to infinity mod psi square dx equals to 1. Okay, so let us see the next one. This one first. Okay. Identify the incorrect statement. Del psi by del x must be 0. Psi x must be continuous. Psi x must be single valued, or none of the above. Yes, there is no such condition. Okay. Okay. Next one. The wave function psi x for an electron is shown below. So let me rewrite this clearly. Psi x equals to 0 for x less than 0 and c e to the power minus x 1 minus e to the power minus x for x greater than 0. If x is in nanometer, c is a constant, then what is the value of c? No, you already have a solution. You already have a solution for 5. Why do you want another solution, right? You just need to use the norm. You just need to use the normalization condition. And since it is between, now it is defined only x greater than 0, so it will reduce to 0 to infinity mod psi square dx equals to 1. So if you do this, you will get C. So please try this. Yeah, please try. Let's solve it. I'll solve it. Yeah. Okay. So yes, that is correct. Okay, so let me just reiterate that. So we have this. So 0 to infinity c e to power minus x 1 minus e to power minus x square, sorry, whole square dx is 1. That means c square e to power minus 2x, and 1 minus e to power minus x square will be 1 plus e to power minus 2x minus 2 e to power minus x is 1. Now c square I'll take outside. I'll just multiply the rest of the terms, e to power minus 2x plus e to power minus 4x minus 2 e to power minus 3x. Now if we do the integration of these, between 0 to infinity, if I substitute the values, c square, if we substitute infinity, all if e terms will be 0, minus, if we put 0, all these terms will become 1. So it will be 1 by 2 minus 1 by 4 plus 2 by 3 is 1. So this gives c square. When we solve this, it will be LCM will be 12. 1 by 12, 1. So c square equals to 12. C equals to root 12, which is 3.46. Answer is C equals to 3.46. Okay, next question. Choose the correct statement. When the particle hits the boundary of the finite potential well, it reflects entirely. Second is E is greater than V0 in Schrodinger equation. The solution exhibit oscillations both inside and outside the potential well. Third is particle hits the boundary of an infinite potential well, it reflects entirely. So, okay, so these are few things we haven't discussed yet. So in we have seen infinite potential well, right? When U is infinity here, U is 0. So we know that psi is only present, psi is only non-zero inside the potential well, and outside it is always 0. Now if U is not infinite, if U is some finite value, let's say U equals to U naught and 0 here. So what happens is psi is not equals to 0 outside also. So basically the wave function that you get. So in this case, the wave function you get are like within the potential well. But here what happens, the wave function that you get are penetrating on the sides outside the potential well, because now the potential is finite. It is not infinite. That means the electron can, or not electron, any particle does have the probability to go outside, right? But where this, if this potential was infinite, that means the particle can never escape this infinite energy. But now it can at times have some energy to go outside, and that's why it's if you plot this wave function, it is penetrating outside x equals to 0 and L also. We have to choose the correct statement. So this one is incorrect, right? Option 3 is correct, yeah. Second is also correct. So okay. So let's say if your particle is inside the potential well, let's say this is finite, 0. So you have seen like it it it, it will, like, if let's say it strikes here, some part of it will if it's a wave, some part of it will reflect and some part of it will transmit, because it is a again finite potential well. It's not infinite, so the particle can transmit the finite potential well. But if the energy of the particle is much higher than u0 or u0, then there is no effect of this potential well, right? It will just keep oscillating throughout as if there is nothing. It does not matter to it what potential here it is, because its energy is already greater than u0. So it exhibits oscillation both inside and outside the potential region. Yes. Yes. There will be reflection plus transmission. But here, this case is E is less than u0. This case is E is greater than u0. What? Yeah. Uh, okay, so yeah, it is kind of outside the potential, right? Just let's say we are defining the potential in terms of x here. X equals to 0, x equals to L. So its position might still lie between x equal to 0 and L, but since its energy E is more than this u0, it does not matter to it, right? So that is what the question says. Oscillation both inside and outside. So inside here means that it can still be between x equal to 0 and L, or can be outside this region. It will have the same behavior. First option was when the particle hits the boundary of the finite potential well, it reflects entirely. So it does not reflect. Yeah, there will be transmission also. Okay, so let's take one more question related to this. So for an electron with 60 electron volt energy, so this is the energy of electron E equals to 16 eV, encountering square barriers. So first barrier is, let's say, let me draw it here. It is 70 eV, and this is, let's say, okay, let me draw it like this. 70 eV, and this thickness is 1 nanometer. Second one is 80 eV. This thickness is 2 nanometer. So a particle is coming from here. You have to tell in which case it has more probability of tunneling through, like some part will go inside and pass through it. In which case that is more probable. That is the question. Yes. So the tunneling probability actually depends on both the energy of the barrier as well as the thickness of the barrier. So this is given mathematically as we can write transmission coefficient is e to the power minus 2 gl, where L is the thickness of barrier and G is the, like, your wave vector term. So G is under root 2m. Now instead of E, it is E minus, sorry, It is U0 minus E upon H cross square. So here is the energy dependence and here is the thickness dependence. This is like we defined uh, the momentum vector K, right? K equals to under root 2 me upon H cross square in the infinite potential well case. Do you remember? So similar to here, it is 2m u0 minus E because now u0 is not equal to 0. Earlier we is not equal to 0. So in infinite potential well case, we had only considered for u for the case where u is 0 between 0, x and L. So we got K equals to under root 2 me upon H cross square. Now u has finite value, 70 V or something. So your G is like this. Okay, so it is not important to like remember this formula, but the main thing to note here is there is this energy dependence and there is this length dependence in the tunneling probability or the transmission coefficient. Your tunneling probability is dependent on transmission coefficient. There is like proportionality, direct proportionality between these two. Okay, so in case one, your G will be something 2m upon h cross square. 70 V minus 60 V is your E upon. Okay, so if I write this thing as a constant, it will be, let's say, under root A times 10, and in case 2, right, it is G is A times 20 under. And now your transmission coefficient T is e to the power minus 2GL. It is e to the power minus 2 under root A times 10 into 1 nanometer, right? Whereas in the second case, it is e to the power minus 2 under root A times 20 into 2 nanometer. Now, so this is obviously a smaller value because it is e to the power minus of this. E to the power minus of something, some bigger quantity will be a smaller quantity. So this is larger. So the tunneling probability in case 1 is larger. Is this clear? So this was mathematically, but it is very intuitive, as you said also. So if it is like thinner and shorter, it is easy to pass through it. Yeah. So it is case 1. Okay, so let's take another question. Okay, this one. No, this is again for infinite potential well. What? Psi square? Okay, this. So this is true for all the cases, for finite and infinite all. This is like a general statement. This is not specifically for infinite well. This is for all the cases. So, but here we are talking about the energy. Okay, so here we are talking about the energy which we had specifically defined for the infinite potential well case. So energy we had defined is E equals to h cross square k square. Sorry, it was h cross uh, n square pi square h cross square upon 2ml square, right? Which we got from by equating k equals to under root 2 me by h cross square and k equals to n pi by l. When we equated these two, we got this E for the infinite potential well. Now we have to find what is the least amount of energy that a particle can have in an infinite potential well of L is 10. Mass of particle m is given and h is also given. So this h cross is actually h upon 2 pi, and this h is the Planck constant. And since it is saying the minimum least amount of energy, so for least amount we will take n equals to 1. Because it has asked for, yeah, least amount of energy. Okay, so your equation now is E is pi square h cross square by 2 ml square, and if I substitute this h square h bar is equal to h upon 2 pi pi square h square upon 2 pi square, sorry, 2 square pi square, and this is 2ml. Yeah, so this pi square and pi square will cancel. We will get h square by 8 ml square. So this is the least amount of energy. Now we just put the value here. But again, so one thing you need to note here is if you put this h directly, it is in joules second, right? So you will get energy in joules. If you put this is if you put this in joule second, so you need to divide it by electron charge of electron to get it in electron volt. So your this will become as 6.626 into 10 to power minus 34 whole square upon 8 into mass of electron is 9.1, 10 to power minus 31. L is 10 nanometer, so it will be 10 to power minus 8 meter square, and then the charge of electron 1.6 into 10 to power minus 19. So now it's just calculation, and if you calculate this, you will get E as 0.376 electron volt. Okay, so this question clear? Yeah. Yes. Yes. Because okay, okay, So what it means is, so your psi was what? Under root 2 by L sine n pi x upon L. Okay. And your E was n square pi square h cross square upon 2 ml square. Now what does this mean is we can define the probability of, so one thing this means is, uh, firstly there's only these discrete energies are allowed, right? Which are like n equal to 1, 2, 3, what you can put, but only those energies levels are allowed. N equal to 1, n equal to 2, n equal to 3, or something like that till infinity. And how the wave function looks like them is between this. So if I put sine, it will be like this, then maybe 3 times or something like that. Now, uh, I think now this is like explanatory, right? This n equals to 1 is the minimum energy. Below that, there is no other defined levels. Above that, yeah, it is not about, I think, multiple waves. So it is just about like this is the minimum energy level that is allowed for this for these particles to stay in. It can either stay at this energy, let's say corresponding to this, which is just found. It is, let's say, 0.376 electron volt. For n equal to 2, it will be uh, like four times 0.376. Here it will be 9 times 0.376. So only these energy levels are allowed for your electron. Since we are talking about electron now, right? This was electron mass we all taken. So the electron can be there only in these allowed energies. So that is why if you see also the EK diagram for an infinite potential well, uh, so we know EK looks something like this, right? What we have seen till now in books. But this is actually for finite potential well, or not also finite. It is for, yeah. This is actually for a whole lattice that we see. Okay, that is, it is continuous because waves uh, superimpose with each other, and it is also, the potential is also not infinite. So because of all that we get a continuous EK. But for a, if U is finite, sorry, infinite, then your energy is discretized. Energy is proportional to n square. Energy is not continuous. So we get only some energy levels, or your EK is actually, instead of this continuous curve, it is like these dots is your EK. Yeah, only if some energies are allowed. So your EK is not continuous. If E is not continuous, that means your EK is not continuous, right? Okay. So is this question clear? Okay, I think we can take one more question. So I think this was from your current assignment. We have to determine the magnitude of potential energy for a particle at x equals to 0, given its mass is m and the total energy of the particle is 0. And the psi x equation was given to be something like this: a e to the power minus x square by L square. Okay, so to solve this, let's first see the Schrodinger's equation again. Your Schrodinger's equation is minus h cross square by 2m. What? Okay. So now the question says you have to find the potential. This is kinetic energy, this is potential energy, right? And this is your total energy. Now it is said the total energy is zero. This means this part is zero. So your potential energy U psi will be equals to h cross square by 2m del 2 psi by del x square. So basically what you have to do to find the potential energy, you substitute this psi x. So in the question it is given that the total energy is zero and you have to find this potential energy U of psi. So if we just rearrange this, your U of psi will be just this part, right? Yes. What do you want me to repeat? Yes. Yes. This is not del, this is U of psi, right? This is potential energy. This is what we have to find. This is what we have to find. So if total energy is zero, that means your potential energy should be negative of Ke, right? That is what we have done here. So now to find this, we just have to substitute psi from here. Then we will get our potential energy. And then we also have to put x equals to zero. That means we will get a function of u psi as a function of x we will get. Then if we put x equals to zero, we'll get the desired potential energy. Yeah. So do you want me to solve it or are you doing it on your own? Okay, so try it. Okay, it is like it involves multiple differentiations. So take care of that. Try it, then we'll solve it. Um, what did you say? A into minus x. Okay, let me solve this. I don't know. I'll need to solve also. So first let's solve what is d psi by dx, right? Which is del by del x of a e to power minus x square by L square. So a I can take outside. So it will be a e to power minus x square by L square into the derivative of this term, which is minus 2x by L square. So your del x del psi by del x is minus 2a by L square x e to power minus x square by L square. Now if we have to do del 2 psi by del x square, that means we have to take its derivative again. Now we have two functions of x that we need to derive, this one and this one. Okay, so again, yeah, let's do u and v. This is u and this is v. So f of uv is u dash v plus v dash u. Okay, so it will be minus 2a by L square. This is u dash v plus v dash will be again 2x upon L square. Okay, so yes, so we can take minus 2a by L square. Yes, yeah, 2x square. Yes, sorry. So this x and x will multiply, right? Okay, 2x square by L square. Okay, so this is your final del 2 psi by del x square. Now we just need to multiply that. What is it? H square by 2m. H square by 2m del 2 psi by del x square equals to minus 2a by L square. Okay, now this is our u psi, u of at x. Now we have to put x equals to 0. So if we put x equals to 0, this term will become 0. E to r this will also become 0. So we'll be left with cos square by 2m 2a by L square. This 2 or 2 will cancel. We can get minus h cross square a by ml square. So this will be the potential energy. Okay, so it's a simple question, just requires h square a by ml square. So it just requires to carefully take the derivatives and all. These kind of questions you will find. So I would just say practice these derivations and everything, practice these derivatives and integral basic formulas so that you are able to solve them. Is there any doubt here? Okay. So these are all the questions I had for today. Mm, If there are no doubts, we can close the section session and we will meet next time. Uh, I don't know, like as I told you before also, right? So the whole course is important, but uh, it will be more like your assignment. So practice your assignments well, and you don't need to like go through all the derivation, but you just like see the basic theories, and there are a lot of almost half the segment every time is theoretical, just theoretical and reasoning, and there are not many numericals. Yeah. No, I don't know that. I don't know exact date, but it will probably be one or 2 weeks after. Like it will be within April, I think. Uh, I don't know the exact date. Yeah, maybe 1 week or 10 days after your last week assignment ends. So after 12 weeks, there will be no extra class. I think there will be one class for summarizing and maybe covering an entire overview of the course. But you can ask your doubts there also. And but after the last week date, I think after April 16, there will be no classes. That is last date for any classes. Okay, so thank you for joining. Let's meet next week.